Okay, so today we will discuss the implementation of Deutsch Josza algorithm in Qiskit. And let me just briefly show you the algorithm before I start implementing in Qiskit. So if you remember from the last class that Deutsch Josza algorithm was essentially this circuit that is given here. This one, and that we initialize all qubits to 0. Then we apply the Hadamard transform, which is essentially the Hadamard gate on each qubit. And then we have our phase oracle. Phase oracle implements a function which is one of the two types. It's either a constant function, which means that f is 0 for all inputs, or f is 1 for all inputs. So it's a constant function. The second option was that f is a balanced function, that for half of the inputs it gives 1, and for the other half of the inputs it gives 0. And then we apply the Hadamard transform again and then do the measurement. And our claim was, if the result after the measurement is 0, it means the function was the result was a 0 state. It means the function was constant. And if the result is anything other than 0, it means the function was a balanced function. That's what we discussed in the algorithm. And today we will implement. And just a word of about implementation of a phase function. We discovered yesterday that we can implement these phase oracles using essentially circuits of this type, that we have several qubits, and then there is an auxiliary qubit which is set in this minus state, and different balance function essentially means applying different combinations of these cx0, and that's it. If you change the location of cx0, for example, from here to here, and you implement another cx, all you do, it is still a balanced function. The only difference will happen that these 4 combinations for which you get a minus sign, they change. Like if the one gave you f of is equal to 1 for this and this, adding another one might give you 1 for this or this input, and so on. So we can also have an x gates before this C0 gate, and that can change again these x's for which the output would be 1. But all of these implementation will still keep it will still make it a balanced function, because half of the input will map to 1 and the other half will map to 0. So we will implement balanced oracles using this function. So this x is not needed, as we will work with this keeping in -1 and nothing doing to it except a control x. Okay, so let me unshare this thing and share my screen. To start implementing this function. Okay. So there are 2 ways for me to show the implementation of the circuit. One is that I walk you through the program that I have already written, and the other one is where I write the program myself. I wrote the program, myself in the last couple of sessions, but from now on, I can prefer walking you through the program that I have already written and sharing the notebook with you. But if you feel like that you will get better if I keep typing in front of you, then please do let me know. Okay, so let me see if I should increase the size of this thing. Okay, so I will increase the size a little bit so that you can read it easily. So this first, box, input box, has just usual imports. I'm importing quantum circuit, execute, air, basic air, and plot histogram. And of course, we need numpy many times. So let me shift enter this one. So this is a star, so it's still running. Now here I have constructed two constant oracles. So this first oracle, I'm calling it F0 all X. Okay. This means that this will implement a function f is equal to 0 for all x. So what type of oracle this should be? This should be an oracle that whatever the input is, the same goes at the output, because f is 0. So if f of x is 0, minus 1 raised to power 0 is 1. So no phase is being added to the input. So essentially, that is all that there is. So let me take this thing out and run this. And you see, this oracle is nothing but just 4 qubit as it is, because whatever is at the input, the same is at the output. Okay, so everybody's okay with this oracle for f of x is equal to 0. Perfect. All right, so let me add another cell at the bottom and paste the other part here. So this is an oracle that I have created for f of x is equal to 1, which means that since f of x is 1 for all x, so for all inputs, I should get a minus at the output. So let's see what there is. And now you see that instead of inverting my 3 working qubits, q0, q1, 2, I have inverted the auxiliary, the ancilia qubit. And the reason is the same as I discussed at the end of last lecture, that in quantum mechanics, the global phase, which appears, in front of 2 product states, can be thought of with any of the, state. So if you think of this q0, q1, q2 as one state, and this q3 as the other state, this x is going to add a minus sign if this q3 is in the minus state. So it doesn't matter if you put these 3 in x and don't do anything to q3, or if you put x here and don't do anything to q0, q1, q2. Since if we put x in front of these 3, it would be, a little bit of overdoing. We will have to execute 3 x's instead of just 1 x. So that's why it's preferable to implement f of x is equal to 1 oracle with an x on the ancilia qubit instead of x on the working qubits. So is this okay? All right, so let me go to the next part now. Now this is a part where I construct an oracle which is 0 for half of the input and 1 for the other half of the input. So let me just write a comment that this implements an f of x is equal to 0 for half of inputs and f of x is equal to 1 for the other half. Now I have prepared 2 strings. So this is a string 101, and then this is I'm calling it Qiskit string, and you will just see the reason for this shortly. And then I have a CX gate string, which is again 101 for the moment. And let me take this part to a part in the next part for now. So now I have after this is that what I do that I implement this loop for over these X gates, this string, and I say that whenever this X gate term is 1, what you do, you implement an X gate. And for the CX gates, I do the same. I run a loop over the CX gate string, and I say that whenever it is 1, implement a CX which is being controlled by M, but all CX are being implemented on the nth qubit, which is the Ancilia qubit. And then at the end, I have to apply X gates again, just because I want the same input, same output as the input on the 3 working qubits. And let's say I have a barrier here, but let's remove this barrier. So let's run this. This is the circuit. Let me draw it MPL. Now you see, this is my oracle. And as you can see that this implements some combination. I'm not worried about for that right now, but this is a balanced oracle because it's implementing these control X gates. And you see that for all of these control X gates, I'm putting an X gate before and after, just, you know, to get different combination. What you can do, you can also have, let's say, some control X without any X before and after, and some control X with some, you know, X before and after. That's up to you. You can have various combination here, and the number where you want to put this CX gate, you can choose this with string. I mean, these are only 3 qubit. If you want, you can do it without any loops as well. You can just, you know, encode directly. You can apply this CX on these 2 qubits, and this CX over here, and this X over there, etc. But you know, this is a little bit a nicer way, and also scalable very easily, because if you have to make a circuit for 10 qubits, you know, it's much easier to define these strings for X gates and control X gates, and say, okay, you need a control X gate at this place, and an X gate at this place, and this can give you a balanced oracle like this. We have an activity where you're supposed to make a balanced oracle that you know, transforms minus with minus sign for particular inputs, and other 4 with a plus sign. So then you will have to think what combination of X and CX gates you have to use. But for now, I'm just you know, giving it as a general one, so you can take any one. Okay, so this is a balanced oracle. And let's now go to the Deutsch Josza circuit. So this is a circuit again that have n plus 1 quantum bits. And let's say I put n is equal to 3 here again. So it has 4 qubits, and it has 3 classical bits. So in a quantum circuit, I can specify the number of classical bits and number of qubits. By the way, if you just give only one input, then by default it will consider them as qubits, not classical bits. All right, so this circuit is actually really simple. What you have is a loop that I have this variable qubit. You can have it I, j, k, doesn't matter, but qubit, you know, as a variable looks a bit nice here. So in the range n, if n is 3, qubit will go from 0, 1, and 2. So in Python, index starts at 0, and when we say this range, it goes to n minus 1. So this is 3, so it will go to 2. So 0, 1, 2. So at these locations, I'm applying a Hadamard gate. You can see here. So I have this series of Hadamard gates, and then you know, this is the part with just let me make here. This is DJ circuit. DJ circuit. And you can see that these 2 commands simply put this nth qubit in the minus state, because first I do this X gate, X, because by default each qubit starts in 0 state in Python. So this X makes it 1, and then this Hadamard H, it makes it minus state, because 1 goes to minus under Hadamard. So this, you know, transform my last qubit, which I will use as an Ancilia qubit, into the minus state. And then let me add this barrier for visualization help. Okay, so let's remove this. All right. Now you see, this is a nice way of adding oracle right here. And all I'm doing, just specifying which circuit that I have already defined here. You see, I have given names to different circuits. So this is F01 half. So this is my balanced circuit. This F1 all X is my one constant function, and F0 all X is my other constant function. So over here, I can choose whichever I want. So let's say first choose F1 all X, and then I just put this barrier for visualization purpose. Now, once I have introduced this oracle in my circuit, in this DJ circuit, I'm putting these Hadamard transforms again. So this is just the repetition of the same loop that I had over here. Again, this is a 3-qubit circuit. You don't really have to use loops. You can, in 3 lines, just specify Hadamard on 0, Hadamard 1, Hadamard 2, and that's it. But, this is a little bit scalable, that later on, if you need to increase these n, you can just, this will automatically scale to the larger value of n. Okay, and then at the end, I add these measurements, and you see, for measurement, I need to specify the qubits and the classical bit, that I measure ith qubit, where I is going from 0 to n minus 1, because this is range n. So when I give range n, in Python, it goes from 0 to n minus 1. So my 0 to n minus 1 qubits are being measured, and their results are being copied to the classical bit, corresponding classical bit. So let's run this circuit. So here is the circuit, and you see that this is the Hadamard transform part. This is the part where my qubit ancilia is going from 0 to minus, and this is my constant oracle right now, because with f of x1. So I'm just flipping this one, which is equivalent to flipping these 3. And then I have these Hadamard and then these measurements. These barriers are just for visualization purpose and doing nothing. All right, so let me stop here and ask if there is any question. No? All right. So let me just show you. If, for example, I add an F01 oracle here, which I have given a name F01 half. Let me check. Yes, F01 half. So if I use this, then this is my circuit. Okay, this part here between these 2 barriers is the balanced oracle. Anyway, so let's now simulate it. And for simulation, I'm using the same structure as before. I have, I'm going to first use this COSP simulator, which is the simulator provided by IBM. And then I'm specifying number of shots as 1024. There's no reason to have, it as a 1024. You can have it as 1000. But since a lot of people are coming to this quantum computer programming from computer science background, so some people, prefer to go in power of 2. But, you can specify these number of shots to, any value you want. Okay, and then I have this job that I'm calling this results. So this results will execute this DJ circuit with the backend that is over here with shots equal to 1000. And I'm collecting the result from this and putting it to results variable. And from results, I'm getting counts. We can get other things from results as well, which I will, also do in due course. But right now we are just interested in counts, and then I'm plotting it using histogram. So let's see what output we get. Okay, so we got 101 state at the output with 100% probability. So this means what? This means that the oracle that was implemented was a balanced oracle, because I'm getting something other than 0. If I had specified here, let's say F1 for all X, this one. So now I have a constant oracle. Let's see. So you can see my output state is 000. So this 000 state is coming with 100% probability. So which means that my computer has found that my oracle is a constant oracle. So any questions so far? Perfect. So Obadallah, you have raised hand. Please go ahead.
सर जिस तरह आपने अभी F1 all x के सर्किट के साथ रन किया ना, के ऑरेकल के साथ रन किया ना, तो सर F0 all x के साथ कर सकते हैं वो? मैं
Yes.
want to see what
So
happens.
for F0 all x, so I have this circuit with nothing happening to these input qubits, and again my output state is 0 0 with the 100% probability. So it means that my oracle is a constant oracle.
Okay, sir. Thank you.
Okay. Perfect. So any other question?